All right. All right. So let's say I'm gonna put a x and y axis here. And by the way, everything we're about to do applies to 3 dimensions. So our goal is if we have a small element here and it's subjected to some stress sigma xx, that's going to be some shear stress sigma x y because it's on the x plane but in the y direction, and similarly sigma yy sigma yx, right? And that could be applied to 3 dimensions. And so what we want to do is relate these stresses to if we were to rotate this element to some new orientation. So we'd have some new sigma x prime, and so on and so forth. So we're going to have some new stresses here. So different magnitudes of stresses that we want to figure out and be able to relate. So ideally, if we knew, say, the stress components for this orientation, and we knew the new orientation, like how we're rotating it, how much we're rotating it, we want to be able to figure out this new state of stress for this new element here. All right. So one of the ways we can relate different and changing orientations is with an equation that is going to be f plus q f prime. And so what is f in this case? Well, f is what we will call a traction vector. And so, for instance, in this cube I'm going to take, we would have some sigma xx, and then some normal stress sigma xx, and then some shear stress sigma xy. And so the traction vector is really just the combination of those. So we kind of add up sigma xx and add up the shear stress sigma xy to get a new vector we're calling t, which is the traction. And we can kind of think of that as this marker here. So if I apply a force upwards, and then I can also apply a force kind of outwards. However, if I do those at the same time, it's going to kind of move at a diagonal here, right? So even though I'm just pushing up and pushing sideways, it is going to move at an angle as if I was pulling on it this way. So similarly, yes, you have normal stress and a shear stress. However, the block kind of feels, at least on this face, as if there is a force, just one force, kind of pulling it up and to the right, in this case, for how I drew it. So yeah, the traction vector is just the combination of normal and shear stress. Okay. And so, right, so F and T are really just the traction vector. So I'm just going to call this F. So F is the traction vector. And then we also have another equation that can relate the normal stress to the traction. So if I have a cube here, I call that normal, and that is a direction. So that is a normal direction, normal to this face, and then also this new orientation of n prime, so the new normal face. And this is a vector, so it's going to have x, y, and z components if I'm in 3D. If I'm just working with a 2D problem, it's just going to have x and y components. Okay. So, equation relating, I guess, this traction force to the normal forces is going to be traction vector is equal to sigma times n. So for instance, if I knew the sigma here, say the normal stress and the shear stress, because again, the sigma is a matrix for a 2D problem. It's a 2x2 matrix, having all 4 of these elements. In a 3D problem, it's going to have 9 elements, so it's going to be a 3x3 matrix. And then if I know this normal direction, I can use this equation to get back the traction vector here. All right. So our 2 big equations are this and this. And you might be saying, what the heck is Q? Well, Q is a matrix dependent on how we rotate it. So whether or not we rotate this going from here to here, kind of this direction, how much we do it, in the z direction if it's in 3D. And so what does that look like? Well, Q is going to be y prime times I, j prime dot I, k prime dot I, so on. And so this Q matrix here, which is a 3x3 matrix, it will change depending on the new orientation I'm trying to find, right? And so what is I prime? Well, I prime is the x component, or the I component of this normal vector. So that distance is I prime. And so what is I? Well, it's just the x component of this original normal vector. So j prime is the y or j component of this new normal vector. So this distance here would be j prime, and k prime is the k or z direction. All right. And so if we want to relate, so we can write, so F equals the sigma matrix times normal direction, but we can also write F prime being the new traction vector. So go to sigma prime, the new state of stress of this element here, times n prime, the new normal direction. Okay. And so now what we can do is substitute F equals sigma n into here, and F prime equals sigma prime n prime. Substitute F prime into here, of this equation. So what we will get is sigma n being a vector again, is equal to Q, it's a big matrix, 3x3, sigma prime n prime, sigma is also a matrix. Okay, so almost there. So we want to, again, our goal is to relate sigma to sigma prime. So if we knew the stress in this stress state of this element, we can find the stress states of this new element in any new orientation. And so we want to get rid of these n normal vectors. So the way we can do that is actually by this equation again, because this equation applies to any rotating coordinate frame, really. And so we can write n is equal to Q n prime. Sorry, that's a vector. Should not be there. It's n prime. So n equals Q n prime. And this Q is the same thing as this, as all these other Q's that we're working with, because, well, we're still working with the same face here, right? It's, again, Q is the property of, or a matrix dependent on how we rotate it. So whether or not we're talking about force, the traction vector on this plane versus this plane, Q is still going to be the exact same because we're, comparing the same plane. Right. So now we can take this n and substitute it into here. So what we'll get is sigma times this part. So q n prime. Keep this right hand side the same. Yeah. All right. Okay. So now we have n prime on both sides. So what we can do is we can kind of cancel those out. You have to be careful with this because, yeah, we also have a q on both sides, but given the way this is written, we are able to cancel these n prime vectors out of here. So then now what we have is sigma times q equals q sigma prime. Okay, and if we want to get sigma prime all by itself, we have to, in essence, get rid of this q. So the way we can do that is multiply both sides by the transpose of q. So what that will look like is the transpose of q sigma times q is equal to transpose of q sigma prime. All of these are matrices. All right, so we just multiply this equation, both left-hand and right-hand side, by transpose of q here. And as you know, transpose of q times q would just be an identity matrix I, which times some matrix, in this case sigma prime, is still just sigma prime. So this whole side here is just sigma prime. So what we get as our final equation is transpose of q sigma just q is equal to sigma prime. All right, so we know the stress here, let's say. So we know this sigma matrix. We know in what way we're orienting it. So we can find q via this equation. And we can just find q prime, or q transpose from q. And therefore we can find the new stress states on this element. So the new normal stress, shear stress on all the planes from this equation, which this might seem familiar if you know Moore's circle, because Moore's circle also relates the stress. So Moore's circle, something like this. It can also relate the stress from some element to some new element through some angles, let's say. However, Moore's circle might be better in this case than using this equation for 2D, because this equation, every time you want to find the stress and a new element, you have to find a new q, because again, q depends on the direction, how much you change its orientation from the original state. Whereas Moore's circle, you can easily find the stresses at really any angle quite quickly. However, in 3D, this equation might be more useful because while you can use the 3D versions of Moore's circle to find the new stresses, if you rotate in 3 dimensions, this equation might turn out to be a little easier because it's still quite cumbersome with